Hello students, welcome to EPG Pathshala. I am Dr. Kajal Chandal from University of Delhi. Today we are going to discuss about the module D to A converter continued from paper measurements and instrumentation. So students, let us see what we are going to learn in this module. Firstly, in this module, the various digital to analog conversion networks are discussed. Secondly, the performance characteristics of digital to analog converters are explained. Then, analog to digital conversion is explained using simultaneous A to D conversion process for 2-bit and 3-bit digital outputs. Finally, A to D conversion using the priority encoder is explained. In the previous module, digital to analog conversion using the variable resistor method and binary ladder or R2R ladder method was discussed. R2R ladder method is preferable in comparison to the variable resistor method. Therefore, in this module, various digital to analog conversion networks are studied where a binary ladder is integrated with an operational amplifier to perform the required digital to analog conversion. Let us study the various D2A converter networks. The figure below shows the diagram of operational amplifier connected as a unity gain non-inverting amplifier. As already discussed in previous modules, the operational amplifier works as voltage follower in which the circuit has a high input impedance and the output voltage is equal to input voltage. It is therefore a good buffer amplifier for connection to the output of resistive ladder. It will not load down the ladder and thus will not disturb the ladder output voltage. The output voltage of ladder VA will appear at the output of operational amplifier. In another network, let us say a feedback resistor R is connected in the operational amplifier as shown in the figure below. In this case, the circuit works as an inverting amplifier that acts as current to voltage amplifier. That is, the output voltage VA is equal to the negative of input current I multiplied by R. The input impedance of the circuit is 0 ohms. Thus, when it is connected to an R2R ladder, the connection point is virtually at ground potential. R2R ladder will produce a current output I, that is the binary weighted sum of the digital inputs. That is, MSB produces a current of V by 2R. Second MSB produces a current of V by 4R and so on. So, total I can be written as V by 2R plus V by 4R plus V by 8R plus V by 16R plus so on till V by 2 raised to power n into R. Since the ladder output is connected to the inverting input of op-amp, so the output voltage will be minus R times the current I. That is, VA will be equal to minus R into, within the brackets, V by 2R plus V by 4R plus V by 8R plus so on till V by 2 raised to power capital N into R. This can be simplified to obtain VA to be equal to minus of V by 2 minus of V by 4 minus V by 8 minus V by 16 till the last term being minus V by 2 raised to power capital N, where N is the number of bits. This expression is same as that obtained from the output of binary ladder, which was discussed in the previous module, except the negative sign. Thus, digital to analog converters in the form of voltage follower and inverting amplifier will provide the same output with a change of sign. However, the voltage follower based DAC works in voltage mode, whereas inverting amplifier based DAC works in current mode. We will now take up the D2A converter IC. D2A converter is available in IC form as the Precision Monolithics DAC 100. It is a 8 or 10-bit D2A converter which is available in 16-pin dual inline package. It uses transistor as current source switches. In addition to a thin film precision R2R ladder network. Figure below shows the block diagram of DAC 100. We can notice in this figure that the IC operates in current mode and is based on the complementary logic. That is, all zeros at the input will produce the full-scale output at VA, while all ones at the input will produce zero output. Let us discuss the performance characteristics of digital to analog converters. The first one is the accuracy. It is one of the most important aspects of digital to analog converters. Accuracy is a measure of the closeness of the actual output voltage to the theoretical output voltage. It depends primarily on the accuracy of the precision resistors used in the ladder and the precision of reference voltage supply which is used. As an example, consider that a particular digital input should result theoretically in an analog output of plus 10 volts. If the range of actual output voltage lies between 9.9 volts to 10.1 volts, then the accuracy of digital to analog converter is accuracy equals deviation in actual output voltage from the theoretical value, which is delta V, divided by the theoretical output voltage into 100%. For the above example, accuracy is equal to 0.1, which is the deviation in output voltage, divided by 10 into 100%, which corresponds to 1%. Another important characteristic of DAC is the resolution. Resolution is the smallest change in voltage that can be distinguished. That is, it corresponds to the increment in output voltage which is determined by the LSB. Thus, resolution of a D2A converter depends on the number of bits in the digital input signal. If the number of bits are large, then the output voltage due to LSB will be small and hence is the resolution. For example, consider a 4-bit system with the input voltage of plus 16 volt. Since the LSB has a weight of 1 by 15, therefore, a change in LSB will correspond to a change in output voltage by plus 1 volt. So, this minimum in output voltage, that is plus 1 volt, is the resolution of the D2A converter. The output will change with digital input in steps of 1 volt and will be in the form of a staircase as shown below. If we want to generate an analog voltage of 4.8 volt using this DAC, we will obtain the corresponding output of 5 volt. It is important to mention that the resolution and accuracy in a D2A converter system should be compatible. That is, if we design a D2A converter with an accuracy of 0.1%, then for 16 volts, the accuracy will be 16 millivolt. However, it has a resolution of 1 volt, which makes the accuracy unjustifiable. Thus, the resolution and accuracy should be kept compatible to each other. Let us next take up the analog to digital converter. Analog to digital conversion involves the conversion of analog voltage into an equivalent digital signal. A number of methods are used for analog to digital conversion. However, the simplest one is the simultaneous method. It is also commonly known as flash ADC, as it has a very fast response and is thus the fastest method for converting analog into digital. This method is based on the use of number of comparator circuits which are arranged in parallel. Hence, analog to digital converter based on this method is also called as parallel ADC. In general, for n-bit digital output, the number of comparators required is equal to 2 raised to power n minus 1. The analog signal, which is to be converted into digital, is applied at the non-inverting input of all comparators using a single line. The second input is a reference voltage and is applied to the inverting inputs of comparator using a divider circuit. The resistive circuit divides the reference voltage into 2 raised to power n equal parts. The reference voltages are thus equal to plus V by 4 plus V by 2 and plus 3V by 4. The corresponding analog to digital converter will convert the analog voltages lying in the range of 0 to plus V into digital. Let us now discuss the circuit of an A to D converter. An A to D converter, which is drawn using 3 comparators for a 2-bit digital output, is shown in the figure below. We can see that the analog input serves as one of the inputs of all the comparators, whereas the reference voltage is another input to all comparators. If the analog input voltage exceeds the reference voltage to any comparator, the output of the comparator goes high, whereas if the analog input voltage is less than the reference voltage, the comparator output goes low. If the input voltage lies between 0 to plus V by 4, then all C1, C2 and C3 are low. For inputs voltage in the range of plus V by 4 to plus V by 2, then C1 goes high and C2 and C3 are low. For input voltage lying between plus V by 2 to plus 3V by 4, then C1 and C2 goes high and C3 goes low. For voltages greater than plus 3V by 4, all C1, C2, C3 are high. The comparator outputs for various ranges of input voltage are summarized in the table below. It can be observed that there are 4 voltage ranges that can be distinguished by this converter. 4 voltage ranges can be represented by 2 binary bits. The 3 comparator outputs are fed into a coding network to provide 2 bits as shown in the figure below, which are equivalent to input analog voltage. The bits obtained from the output of coding network can be entered into a flip-flop register for storage. The complete block diagram is discussed below. In order to develop a clear understanding of the simultaneous conversion process, let us investigate the 3-bit converter. For a digital signal having 3 bits, 7 comparators are required. This will divide the analog input voltage into 8 ranges. The circuit diagram for a 3-bit simultaneous A to D converter is shown in the figure below. It may be noted that some of the comparators have inverters at their output, since both C and C' are needed for the encoding matrix. The function of the encoder is to take the 7 output levels of comparator as input and encode them into a 3-bit binary number. Let us discuss the outputs of comparators of 3-bit A to D converter along with the encoder output. It can be seen that for an input voltage varying from 0 to plus V by 8, all C1, C2, C3 till C7 are low. For an input voltage varying from V by 8 to V by 4, only C1 is high and rest all others are low. For the input voltage corresponding to V by 4 to 3V by 8, C1, C2 are high and rest all others are low. For input voltage varying from 3V by 8 to V by 2, C1, C2, C3 are high and rest others are low. For the voltages of the range V by 2 to 5V by 8, C1 to C4 are high and C5 to C7 are low. For input voltage varying from 5V by 8 to 3V by 4, all C1 to C5 are high and C6 and C7 are low. For the voltages 3V by 4 to 7V by 8, C1 to C6 are high and C7 is low, whereas in the last range, which is 7V by 8 to V, all the comparators give the output high. The corresponding binary outputs are also shown in the table. It can be seen that the 2 raised to power 2 bit is high whenever C4 is high. So, it is easiest to determine this bit. The 2 raised to power 1 bit must be high whenever C2 is high and C4 bar is high, or I can say whenever C6 is high. Therefore, the expression for 2 raised to power 1 bit is given by 2 raised to power 1 is equal to C2 into C4 bar plus C6. The logic expression for the 2 raised to power 0 bit can be found in a similar way as 2 raised to power 0 is equal to C1 C2 bar plus C3 C4 bar plus C5 C6 bar plus C7. In order to transfer the data from the encoding matrix into register, 2 steps are required. First, a positive reset pulse must appear on the reset line to reset all the flip-flops low. Then, a positive read pulse allows the proper read gates to go high and thus transfer the digital information into flip-flop. Next, we discuss the alternate design of A to D converter. Alternately, the digital logic for conversion of A to D converter comparators into digital outputs can be replaced by a priority encoder 9318 as shown in figure below. Here, priority encoder is used to transform the comparator outputs to the correct digital binary output. The inputs to the priority encoder, that is C1, C2, C3 till C7 must be TTL compatible. The 9318 encoder gives an output on the basis of highest order active input, ignoring all other inputs. The analog to digital converter is advantageous due to the fact that its construction is quite straightforward. Also, it is relatively easy to understand. In addition, it is the most efficient of the ADC technologies in terms of speed, which is being limited only in comparator and gate propagation delays. However, it suffers from a limitation that as the number of digital bits expected in the output increases or the resolution increases, more and more comparators That is, for n bits, 2 raised to power n minus 1 are required to perform the desired conversion. For example, one 3-bit digital out 13-bit for example 13-bit digital output for example 3-bit digital output requires 7 comparators. A 4-bit digital output requires 15 comparators. In general, for an 8-bit digital output, which is preferred for most applications, 255 comparators are required. The circuit in this case becomes very bulky, complicated, and expensive. Another important point to mention is that for equal values of resistors in the resistive divider network of comparators, each successive binary output corresponds to the same increase in analog voltage, giving a linear response. However, the values of resistors can be easily varied to introduce the non-linear property in the output. So, a custom non-linear response can be obtained with respect to an analog signal. This ability of flash ADC to provide signal conditioning behavior by simply changing the value of few components makes it unique amongst other ADCs. This ability of flash ADC to provide signal conditioning behavior by simply changing the value of few components makes it unique amongst other ADCs. Last, we take up the applications of flash ADCs. Flash ADCs are ideal for applications requiring very large bandwidth, but they consume more power and are much bigger in size than other ADC architectures. Motorola MC10319 is an example of 8-bit flash A to D converter. It has 256 parallel comparators which are connected to a precision voltage divider network. The comparator outputs are then fed to latches and subsequently an encoder network that captures the digital signal in gray code. The use of gray code ensures that any small fluctuation in the analog signal is not reflected in the digital output. The gray code is finally decoded into binary outputs. A to D converters are frequently used in applications such as radar signal processing, video displays, high-speed instrumentation, and television broadcasting. So students, let us now summarize what we have learned in this module. Firstly, in this module, the various digital to analog conversion networks were discussed. Then, the performance characteristics of digital to analog converters were explained. Then, analog to digital conversion was explained using simultaneous analog to digital conversion process for 2-bit and 3-bit digital outputs. Finally, analog to digital conversion using the priority encoder was explained. Thank you students for your attention.